There you go. Hey guys, this is Mrs. Tran-Bloom. We're starting section 5.4, logarithmic functions. Okay, I just want to tell you how important this is. Okay, this is probably one of the most important sections out of all the units that we study in pre-calculus. So make sure you guys understand this unit really well. So let's talk about some things that we studied before the break. Okay, recall that 1-to-1 function y equals f of x has an inverse function that is defined implicitly by the equation x equals f of y. Okay, so let's talk about this. Y equals f of x. This is a regular function, right? It has an inverse, which means we are switching. Y is now x and x is now y. So we're switching the variables here. In particular, the exponential function y equals f of x equals a to the x. So this is your exponential function right here, where your base is greater than 0 and a can never ever be 1. Because if it's 1, then 1 to anything, it's really itself. So it's really not interesting. It's 1-to-1, so this is an exponential where the base is greater than 1 and it can't ever, the base is greater than 0 and it can never ever be 1. It's a 1-to-1 function and hence has an inverse function that is defined implicitly by the equation. We're switching y for x equals base is going to stay the same. We're switching x for y. We're going to have to solve for y later, but right now we're going to keep it as is, where again the base has to be greater than 0 and can never ever be 1. This inverse function is so important. It's so important, okay? We're gonna give it a special name. It's called the logarithmic function. Okay, and we're gonna see below when we switch x and y and solve for y what it turns out to be. Okay? So vocabulary and some theorems that we're gonna need to know. The logarithmic function to the base a, where again the base is greater than 0, it can never ever be 1, is denoted by y equals log base a of x, read as y is the logarithm to the base a of x, and is defined by y equals log base a of x. Now this is something that I want you to understand. When you're writing y equal log base a of x, make sure your base, whatever base is, it has to be subscript, okay, of y, of the log of x. If and only if this right here, remember this is the inverse function of the exponential, if and only if x is equal to a to the y. So when you switch x and y in the exponential function, you have to solve for y, and after you're done solving for y, this is what it turns out to be. The domain of the logarithmic function, y equals log base a of x, is always going to be greater than 0. So let's talk about why that is, okay? So let's talk about the domain. So I'm going to focus on this little picture right here, okay? This little picture right here, remember this is y equals, this is an exponential. Let me zoom in really quick, okay? There you go. Alright, so check this picture out. This is y equal, if you can't see that, this is y equals 10 to the x. I know it's kind of blurry, okay? This is y equals 10 to the x. Now this is an exponential function, y equals 10 to the x. When x is 0, y is 1, so that's my first dot. When x is 1, y is 10, so it's up here is my second dot, okay, which for this particular picture it's not sketch. When x is negative 1, y is 1/10. So you're supposed to have 3 dots, remember always. So this is your exponential function. When I switch x and y, this is actually x equals 10 to the y, okay. Now, because it's so important, the inverse, this is the inverse, is so important that it has its own name. It's called y equals log base 10 of x. Or in this case, base 10 is in a little bit, we're going to learn that's a common log, so it's not written. Y equals log base 10 of x. So notice how the points are now switched. This is negative 1 comma 1/10. This is 1/10 comma negative 1. This is 0 comma 1. This is now 1 comma 0. And technically there has to be a third point. Whenever you're graphing, I don't want to see just 2 points. I want to see minimum 3. So over here somewhere, you should have 10 comma 1. Okay, So and if you check it out, it's these two functions are symmetrical about the line y equals x, which is your identity line. That's why these two are inverses of each other, and remember you do have to solve for y, so that's why y equals log base 10 of x is the inverse. All right, now let's back. Oh, sorry, I wanted to go there for the domain. Okay, so remember the exponential function, the domain is all reals. Okay, so that means the range of this is going to be all real. The range of your inverse, which is the log function, is all real. And remember how the range of the regular function, the exponential function, it's greater than, remember there's an asymptote here, it's greater than 1. So that's why the domain of an inverse is greater. Okay, not greater than 1, greater than 0, is greater than 0. Because these two have to switch. Okay, then that means the range of an inverse, which is the log function, is going to be all reals. Okay, so whatever you had for your exponential is now switched for your log function. All right, let's go back and talk about this. Oop, I don't need it that big, so here we go. Okay. So down in the next box, it states the domain and range. Okay, the domain of the logarithmic function equals the range of the exponential, which makes sense. Okay, it goes from 0 to infinity, not inclusive at 0. The range of the logarithmic function, which is the same as the domain. Remember, the domain of the exponential function is always all reals. Okay. The next box. Here we go. Because this right here is the inverse of the exponential function. Now to write it, we have y equals log base a of x. Let's check out the location of this. Your base a remains as base a in the log term. Okay. And your exponential is now the output. Okay, so the exponential is the output. And your output of the exponential is now the input, or the output of the inverse is now the input. So again, the base is always going to be the same. Okay. All right, so, and again, it states the domain and range of the inverse again. The domain is between 0 and infinity, not inclusive, and the range is all reals. Okay, common log and natural log. Now, common log is, the reason they gave it a name is because y equals log base 10 of x. It's so common that we get so lazy, we don't want to write the base 10 all the time, just like the square root of x, right? This is supposed to be an index of 2, but because it's so common that we normally don't write it, so that's why we just write it as a square root. So common log y equals log base 10 of x. Okay, it's usually not written as a base, but we know that it has to be a base 10. Natural log. Natural log has a base e. So natural log is y equals log base e of x. Okay, so log base e is now rewritten as ln of x. Okay, so if and only if x equals to the base e to the y. So when you're rewriting it in terms of log, it's y equals log base e of x, and log base e becomes ln. Okay, so let's recap some properties of the logarithmic function. F of x equals log base a of x. Okay. The domain is the set of positive real numbers, and the range is a set of all real numbers. Okay, so remember, the domain is when x is greater than 0, and the range is all reals. Okay, the x-intercept of the graph is 1. There's no y-intercept, and that makes sense because when you have the exponential, you had a y-intercept at 1, so now it's reversing or switching. The y-axis, which is y equals to 0, is the vertical asymptote. And that makes sense because the exponent function has, you can't really see that, so let me just zoom out. Exponent function has an HA, which is a horizontal asymptote. Okay. A logarithmic function is decreasing, okay, from 0, decreasing if a is between 0 and 1, and increasing if a is greater than 1. Now this is still the same as an exponential function. And let's talk about increase and decrease. Okay. Notice how this is a common log function right here. Notice how this is a log function. And it's an increasing because common log has a base 10. So if the base is greater than 1, then it's an increasing function, which is really no different with exponential. Okay. And it's decreasing if the base is between 0 and 1, not inclusive. The graph f contains the point. Remember, these 2 points now have to be switched from your exponential. The exponential is going to be when x is 0, y is 1. When x is 1, y is a. When x is negative 1, y is 1 over a. Let me move it over. 1 over a. So when you have its inverse, it makes sense that all the x and y values are switched. Okay. The graph is smooth and continuous with no corners or gaps. Again, this is the same property as your exponential. All right. So now I'm just going to flip over to examples. Okay. Let me zoom out so I can see the whole direction here. All right. Example 1. Change each exponential statement to an equivalent logarithm statement, or vice versa. So right now, this is an exponential. So to go from exponential to log, I'm going to write log and then my base. Okay. Well, if you check this exponential, it has a base of 3. So that base of 3 is going to be the same. This is now your output in the exponential, so it becomes an input. And the input becomes the output. Okay. Similarly to this one, okay, I'm going to write log. Your base is 3. And remember, it has to go below the word log. Otherwise, I'm not going to understand. Is this log base 10 of 3 or is it log base 3? Okay, if you don't have, it's not the same as writing this. Okay, these two are completely different. All right, so this log base 3 of, this is your output, so now it's my input equals 4. Okay. All right. I'm going to do this one. Log y equals log base 5 of x. So I know my base is 5. I'm going from log now to exponential. So my base is going to stay as my base. Okay. Then I need an exponent, and then I need an output. Now check this out. This is your input. So now it becomes my output. Oops. Why did I write a y right there? I didn't mean to. I meant an output. So input and output. So log base 5 of something equals to y. Okay. So log base 5 of y equals to x. This is your output. It becomes now my input, and your input becomes the output. All right. Why don't you try this on your own right now? I'm going to give you guys about 10 seconds. Okay. Try it out. Okay, so hopefully you're writing negative 1 equals log base 5 of 1/5. So hopefully you write your base first. Your base is 5 in the log function. It's going to be base 5 in the exponential. This is your output, so it becomes now my input. This is your input, becomes my output. Okay, and 5 to the negative 1/2, it makes sense that becomes 1/5. All right, what I'm going to do here is I'm gonna have you do this one, but watch me do this one first. This is currently an exponential, so I'm going to ask you to write it obviously as log. And so normally I would write log. Your base is e, so I would write e of, this is your output, so it becomes my input, and that's your input, becomes my output. But remember, log base e has its own special name. It turns itself to ln. So this is ln of n equals to 3.9. I'm sorry, it's not supposed to be 39. It's supposed to be 3.9. Okay. You may not leave log base e as log base e. If you see log base e, it becomes ln. Okay, go ahead and do this one on your own. So make sure, okay. So make sure you pause it and do that one on your own. All right, similarly to this, I want you to try this on your own. This is ln of 5 equals y. So think about ln of 5. What is that log base of? So I'm going to even write this out on your own. ln is log base e of 5 equals y. So I want you to do on your own, write it back in an exponential form. Okay, so these two, please do it on your own. All right, so the next one is going to be find the exact value without a calculator. That means no calculator whatsoever. Okay, and again, I want you to pause right now and complete E and G. If you don't do it right now, you're going to forget, and then you're not going to get credit for it. So might as well just pause and finish that up. All right. So example 2. Here we go. Find the exact value without using a calculator. So log base 3 of 81. Okay. So currently I don't know what it is. I'm going to let it be log base 3 of 81 equals to u. Okay. So anytime you have a log expression or a log equation, you can rewrite it as exponential. Exponential. Okay. This is my base, 3 to the u equals 81. So 3 is a prime number, 81 is not a prime number, but I know 81 is 9 times 9. And 9 is 3 times 3. Okay. So it looks like 81 is 3 to the 4th power equal to 3 to the u. Okay. So 3 to the u equals to 3 to the 4th. Well, if the bases are exactly the same, so that means this whole piece, u is 4. So this whole piece turns out to be 4. So my whole answer is 4. Okay, so log base 3 of 81 equals to 4. And normally I would not be able to find the answer, log base 3 of 81, unless it's rewritten as an exponential. Or later, we can learn to do another way with using log. But right now, just rewrite it as an exponential function. Okay. All right, I'm gonna skip that one so you can try that one on your own. Okay, so right now, just set it equals to u. I would like for you to rewrite this. Okay, rewrite as an exponential, and then I would like for you to solve it on your own. All right, so on your own. Okay, so hit pause right now, solve that on your own before you forget. Okay, I'm going to do the next one. Okay, ln square root of e. What is that going to be? So what I'm going to do is I'm going to set this equals to u. Well, square root of e, it's going to be similar to, so ln of e to the power 1/2. Okay, because that's what square root is. You can rewrite square root as a fraction exponent equals u. So from here, we're going to based on the power rules that you have from your exponential unit, ln of e to the 1/2, because this is an exponent, it becomes a multiplication. Okay, so that's the same thing as 1/2 times ln of e equals u. Okay, and again, exponential becomes a multiplication problem. Now, I'm going to prove to you why the answer the way it is. ln of e, it's really unique and it's really special. Okay, ln of e is always 1, and here's why it is 1. Okay, I'm just going to show you why it's 1 before I tell you that you need to remember it. So 1/2 ln is really log base e, right? So ln becomes log base e, and I still have the of e equals u. Okay, I'm going to rewrite this as an exponential. So I'm going to leave out the 1/2 for now. We're going to come back to the 1/2. So this is the same as e to the u. So e to the u equals e to the 1st power. Okay, this is my base. I'm going to write, this is my output, so it becomes the input. This is the input, becomes the output. Currently, this e has an exponent of 1. So currently, e to the u equals e to the 1. So would you agree that u is 1. Okay, so this whole thing right here, guys, becomes 1. So that means ln of e, it's 1. Okay, so ln of e, it's always 1. So this is not our answer, but I want you to remember that. Okay, so if ln of e, so back to this piece, okay, if ln of e is always 1, what's 1 times a half? 1 times a half, it's always 1/2. So this whole answer right here, ln square root of e equals u, that means u becomes 1/2. Okay, and that's why from now on you have to understand that ln of e is always 1. And here's the proof why it is 1. Okay, so now that we know ln of e is 1, so you can write I am ln e, or wait, no, I am number ln e. See, I am number 1. Ha 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 ha. Okay, so now that we know what ln e is, okay, so first you have to, this is an exponential, ln of e to the power of 4. I would like for you to rewrite that. That's 4 times ln of e. And we know that ln of e is 1, right? ln of e, so that means 4 times 1. So ln of e to the 4th comes out to be 4. Okay, so do we know why ln of e is 1? Say it 5 times. I am number ln e. 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 All right. All right, go back and double check this for me. Make sure you're doing that's completed. And let me zoom out. Make sure also, okay, these above 2 problems on your own are also completed. All right, until next time, have a great day.